So here's what we have so far. You can see that? Looks like the flare. Okay, so far in section 8.1, we had sequences. And we said that a sequence converges to a number L if it has a limit of L as n goes to infinity. This sequence converges to L if the limit as n goes to infinity of an is equal to L. That was easy to do. We did a little Hopital's rule. We took things out of indeterminate form. Just same old stuff. Then in section 8.2, we made a couple of series. Where we denote a series with this capital letter sigma. Then we put our general term here. And it means you add things up that look like the terms in a sequence, but now they're added. Checking to see whether a sequence converges is a heck of a lot more to do than just taking a limit of that general term. The limit of the general term tells us very little. We'll see sometimes it tells us something, but most of the time it tells us very little. So right now we have two ways to check if a series converges. One way is to see if the sequence of partial sums converge. If sequence Sn of partial sums converge, say to some sum S, then so does the series. The unfortunate thing is it's often very difficult to write the sequence of partial sums in a closed formula, general formula for Sn. So it is often difficult to get the general formula for Sn. The times where it's not too difficult is if your series is telescoping, in that when you write out all the terms, everything vanishes except for the first term and the nth term, if you talk about truncating it off at n. So if you have a telescoping series, we can do it. And sometimes we can do it just by merely luck. Maybe the sequence of partial sums has a pattern. We just kind of fall into it luckily. It's very hard to do, especially at your level of experience, which is nowhere near mine. But even though I think it's hard to do. But the other type that we can get the general formula for was a geometric series. And we did that in general. So we don't have to do the partial sum stuff for a geometric series. So if you have a geometric series, then we can tell whether or not it converges by looking at some of its features. A geometric series is one where we're adding terms together, but each term is obtained by multiplying the previous term by the same number over and over and over, called the common ratio. So a geometric series can be written in the form as the sum from k is equal to 1 to infinity of a times r to the k minus 1 or k power, doesn't matter which one. And it just looks like a plus a times r plus a times r squared, and so on. Each term again is a multiple of r of the term right in front of us. And these series will converge if that multiplier in absolute value is strictly smaller than 1. If it's 1 or more, then it will diverge. And not only will you know that it converges, but you know what it converges to. That number s that I'm talking about here is the first term of the geometric series divided by 1 minus r. Is that where we stopped? Okay, so let's make up a geometric series, for example. I'll get a couple of them here. The question is converge or diverge. So my first one looks like the sum from k is equal to, we'll start one at 0, because it didn't have to start at 1, to infinity. And let's go with 4 to the k divided by 3 to the k plus 2. Eventually, you'll be able to recognize a geometric series when it's written in summation form, because the variable, the k, the counter, is always an exponent, and the base is always a number. So a number to the variable power is kind of a giveaway that you've got a geometric series. But to make sure that you have one, just run out the first 3 or 4 terms and see that it has the pattern that I've described up there. And start running out terms based upon what k starts with. So here k starts at 0. So my first term looks like 4 to the 0 divided by 3 squared. Now k is equal to 1, and my term looks like 4 to the 1 divided by 3 cubed. Now at k is 2, I have 4 squared divided by 3 to the 4th. So it's pretty easy to see that I move from one term to the next. I multiply each numerator by 4 and each denominator by 3. Agree? That makes that number r 4/3. That's enough. I now know the answer to the question. 4/3 is bigger than 1, so it diverges. This is a sum that's going to grow infinitely large. Okay. Now let me make a slight change. Instead of writing that denominator as a k plus 2, let's write the denominator as k times 2. Here. Keep the counter starting at 0. And I'm going to have 4 to the k divided by 3 to the 2k. So my first term looks like 4 to the 0 divided by 3 to the 0. My second term looks like 4 to the 1 divided by 3 squared. And then I'll have 4 to the 2 divided by 3 to the 4. So what is the common ratio this time? 4 ninths, right? 4 over 3 squared is what I'm multiplying by to move from term to term. So R is 4 over 3 squared, which is 4 ninths. That's smaller than 1. So this is an example of a convergent geometric series. And I know that it converges to the sum of A over 1 minus R. A is the first term. Any number to the 0 power is 1, so my first term is just 1. My R was a positive 4 ninths. 1 minus 4 ninths is 5 ninths. 1 divided by 5 ninths is 9/5. Is that okay with everybody? Geometric series are the easy ones. We're going to see another easy series today. Do you think you have any questions over 8.1 and 8.2?
The only way to find an SM for like an arithmetic sequence that doesn't telescope is to just like try to figure out a pattern.
If you can figure this thing out as a function of n, then you can take the limit of it. All right, so let me keep myself somewhat organized here. I'm sorry? Where do I get the A from? The first term? Whatever is the first term. So here K was 0. I had 4 to the 0 over 3 squared. So my A would have been 1/9. And when K was 0, 4 to the 0 over 3 to 0 gives me 1. So the A is always whatever is spit out first from the formula. Okay, in section 8.3. What is the name of section 8.3? We're going to have 3 big ideas come out of this section. The first one is going to be called the test for divergence. Not a test for convergence, it'll be a test for divergence. The second big thing, we're going to be able to use our integration skills because there's something called an integral test that we can apply to series. And from the integral test, we'll see another type of very easy series to recognize by just a visual approach, something called a P series. So we're going to look at test for divergence. And we'll look at the integral test. And a byproduct of the integral test is something called a P series. Just the letter P, not the dog lift his leg up on a hydrant P. So a good visual of what we mean by a series is to visualize a series as a sequence of sticks of height an for each counting number n. So if my first term was like 4 ninths, then I have a stick of height 4 ninths. And then whatever my second term is, I'll get another stick of a certain height. And then maybe another one. And then maybe another one. And then a series can be imagined as taking each of these lengths and adding them together, or just stacking one stick above the other. And if that stick achieves a height without growing infinitely long, if it just eventually achieves a certain height, then we say that the series converges. But really, the only way that can happen is after I stack my sticks together, that when I'm way down here in my counting numbers, that I'm essentially putting nothing on, right? I'm just putting just little bitty teeny tiny links that don't add any length on. So a necessary condition for a series to converge is that the terms way out here have to go to 0. Unfortunately, that's only a necessary condition. It's not a sufficient condition. So a necessary condition that our series converges is that the terms have to eventually vanish for k big enough. So bigger than some really big number, capital N. That's a necessary condition, but that's not a sufficient condition. There are gazillions of examples of series whose general term goes to 0, but the series diverges. But there's absolutely no example of a convergent series whose nth term does not go to 0. And that's the test for divergence. If you can take the limit of this term and get something that's not 0, you're done. You say the series diverges. If you get something that says the limit is 0, you just say, oh, I don't know. I better try something else. Okay? Or positive term series if the limit as k goes to infinity of ak is not 0, then the series diverges. I'll state parenthetically, if the limit of AK is equal to 0, then we still know nothing. This is definitely not a test for convergence. It's a test for divergence, as the name really, really suggests. Test for divergence. So for example, I look at the series from k is equal to 1 to infinity of k divided by k plus 1. So that's the series whose terms look like 1/2 plus 2/3 plus 3/4 plus 4/5, blah, 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 blah. Adding fractions together that look like that. I know that series diverges because what's the limit of that general term as k goes to infinity? It's 1, right? This series diverges because the limit as k goes to infinity of k over k plus 1 is 1. So that means when I'm adding these fractions together, in the long run, I'm adding a bunch of 1s to the list. So it's going to keep growing and growing and growing. Okay? Okay, the next test. Now assume that you have some terms that in the long run, the length of the sticks go to 0. They could do a little bit of smooth maneuvering at the beginning. That doesn't matter. But once we cross a certain point here, they all get smaller and smaller and smaller. They're all positive. I'm talking about positive term series here. But in the long run, they all get smaller and smaller and smaller. If I can find a function that passes through these points that's continuous, and that I know how to integrate it, then I'm finding the area under that red graph. If the area under that red graph is finite, don't you think that the sum of these little red sticks is going to be finite? Right. If the area under that red graph is infinite, then these sticks will add up to something infinite as well. That's not as clear to see, but that is true. That's the integral test. If I find a function that passes through all of those points at the integer values, and if its integral from whatever the first number is to infinity is finite, the series converges, but not necessarily to that same number. If that integral is infinite, then the series diverges. So let's write down the integral test. This is for the positive term series. Let F be a continuous decreasing function that passes through each AK, K is equal to 1, 2, and out to infinity. Then the series does whatever the integral does. Converges if that improper integral converges, it diverges or becomes infinitely large if that improper integral itself is infinite. It is important that these are all positive term series, because if you start adding positive numbers with negative numbers, you can still get a finite integral. I want to make sure that we have just a positive term series. We also have to make sure that this function is decreasing, not that it goes through so many of the points and then changes its mind. So it's got to be a strictly decreasing function after a certain point. Again, it could do stuff in the middle, but once you cross a certain point, it has to keep decreasing toward the x-axis. It's easy to find that function. For example, a function that passes through all of these points would be f of x is x over x plus 1. You just make a function out of the general term. It contains all the integer values, but it also contains the ones in between the integers. That's why it's really important to know what you know how to integrate and what you don't. Let's look at the function I've got the infinite series. It starts at 2 because the natural log of 1 is 0, and I don't want to divide by 0. Of 1 over k times the square root of the log of k, does it converge or diverge? And when I look at it, I know logarithms, once I pass the k is equal to 1, are all positive. And so all of this stuff is positive. Everything's above the x-axis. So I've got a positive term series. Now I'm going to make a function that I can integrate just by changing the k's to x's. I know this function's positive, again, because I'm only concerned with the interval from 2 on out. I know it's decreasing because I have a constant in the numerator and the only x's are in the denominator. And both things in the denominator are growing functions. So if the denominator continues to grow, the reciprocal will always decrease. Okay? Or another way to say something is decreasing is to show that the next term is smaller than the previous term. If I replace each x with x plus 1, that denominator is bigger than the way it looks here. And so when I take the reciprocal, the overall fraction is smaller. So I'm going to make the note that f is continuous and decreasing. And it's something I know how to integrate. So now I'm going to integrate from 2 to infinity of 1 over x, the square root of the natural log of x. Who's going to tell me how to integrate that? Right, I got a logarithm. I'm going to take u to be the natural log of x. And then du gives me the rest of the integral, the 1 over x dx. There's the 1 over x dx. So I'm integrating 1 over the square root of u du. I can integrate that with the power rule if I write that as u to the negative 1/2 power. So when I integrate that, I get u to the 1/2 power, then I divide by that 1/2, puts me a coefficient of 2 in front. So we get 2 times the square root of u, and u is the natural log of x. We're doing this from 2 to n. So I'm looking at the limit as n goes to infinity of 2 times the square root of the natural log of n minus 2 times the square root of the natural log of 2. What's your conclusion about this integral? It diverges. This becomes infinitely large. So our conclusion about the series is that the integral diverges and so the series does too. That's right. We're going to have so many tests. I want you to make sure that each time you decide whether the series converges or diverges, you explicitly tell me why. Okay. Anytime you test a series and just say converges, and you happen to be lucky and it does converge, but all you said to me was that it converges, you don't get any credit. You got to tell me what test you're using, perform the test, and clearly state the conclusion. That's going to be hard to practice on web work. You know, on web work, you're going to have some series there, and you click a box that says converges or diverges. And you get an infinite number of tries. I think I could figure that one out without even taking calculus. I just keep clicking until I get them all right. But that's not going to help you any. So make sure you know how to perform the steps that generate that conclusion. Okay, so don't take web work as the joke that it is. When you write up the problems for me, put me all the steps in. Okay? Okay, then let's find something else maybe that we know how to integrate. Let's change that from the natural log of k and just put a k under that square root sign. Yes, sir.
We use the test for divergence on the same problem.
But the limit goes to 0. Right? You agree that the limit of this thing goes to 0? This k goes to infinity? So here's an example where the limit goes to 0, but the series diverges. Limit goes to 0 is only necessary, not sufficient. Right? Water is necessary for life, but it's not sufficient. If all you had was water every single day of your life would be pretty short.
If the limit goes to 0, then why wouldn't it?
It's not going to 0 fast enough. Goes to 0 in such a way that the sum still can become infinite. Okay, so now we're going to do this one. Take away the logarithm.
Wait, hold on. That doesn't make sense. How can a series diverge is still going to 0? It doesn't get past it.
The terms go to 0,
Yeah.
but the sum doesn't. So by the time I got out to where the terms go to 0, maybe I've already added an infinite number of links together. Right? That's what I mean by not going to 0 fast enough. Okay, so the next example does do the same for the sum from k is equal to 1. Yeah, I can start at 1 this time. 1 over k times the square root of k. Right, remember in our tower of power how slow logarithms were? And k was, square root of k is going to be a little bit faster. So this one's going to converge. I just let the old spoiler alert out. We're going to take f of x be 1 over x times the square root of x for x greater than or equal to 1. And since the only x's again are in the denominator, and I'm away from 0, this is a continuous decreasing positive function. So now we're going to integrate from 1 to infinity of 1 over x square root of x. We don't even need to do substitution. Just put those exponents together and put it upstairs and do the power rule on your integral. What's the x times the square root of x going to be? That's x to the 3/2, so we're integrating x to the negative 3/2. Well, actually, I should put a limit here. I get lazy when I do series. Sometimes I forget the limit. Add 1 to the power and divide by the new power, and you'll get x to the negative 1/2 times negative 2. X to the negative 1/2 times negative 2. When I evaluate this, I'm going to take that x to the negative 1/2 and put it in the bottom as a positive x to the 1/2. And now I'm going to put the n in there. And you're going to tell me what the value of that limit is. The integral will be 2. The value of this limit here is 0. So I get 0 minus a negative 2. That means my integral converges to 2. The 2 is the value of the integral, not the value of the series.
So can we figure out like what the series itself converges to? Like the number?
Sometimes, sometimes not. Sometimes the best we can do is some numerical approximation. Sometimes we can for a certain series. But not us. That's not the concern in this class. Now, this is an example of a series that's called a P series. I can write this thing as 1 over k to a power. And the size of the power tells me when this will converge. Remember when we wanted to know when does the integral of 1 over x to a power converge? Didn't we do that one? What made this converge was after I added 1 to the power and divided by the new power, my exponent was negative, so that when I evaluate the limit, I'm able to move that term in the denominator. So what size does the exponent have to be in this position so that after I move it up, integrate by adding 1, it's still something that's negative?
What's the negative?
It has to be smaller than,
Negative 1.
well, when it's down here, it has to be smaller than, has to be bigger than 1. Bigger than 1, right? Because when I move it up, say here it was 3/2, I moved it up so that when I added 1, then it was still negative. But if this is smaller than 1, say this is just a 1/2. When I move it up, it's a negative 1/2. When I integrate, it's a positive 1/2. Having this on top, going to infinity, makes the limit grow too large. So this converges only if the power, when it's down in the denominator, is strictly larger than 1. So for our P series, oops, I don't want to say that that's equal to that. That is called a P series. It will converge if P is strictly bigger than 1. And that's what the integral test tells us. If P is 1, you get a logarithm when you integrate, and the logarithm is going to grow. If you get, if P is half, you get a square root on top, right? So you need P to be strictly bigger than 1. It's kind of built in the other direction than a geometric series. The geometric series had the number as the base and the variable as the exponent. The P series goes the other way. The variable's here and the number's the exponent. Okay? Kind of says things backwards too. Remember, geometric series converges if R was less than 1. P series converges if the power is bigger than 1. You remember that? If you can't remember that, just integrate. Bueno? Okay, what else can you integrate? Let's see. How about we see if this series If this K weren't here, that would be an example of a geometric series. Because that would look like 1 over e to the K. So my R would be 1 over e, and it would converge. But the K is there, so it's not geometric, but it is something I know how to integrate. Does it look like something you know how to integrate? Do you first agree that the terms go to 0? Because it's K divided by e to the K. E to the K grows real fast. So you always make that check. Make sure you deal with terms that are going to 0. If they don't, you're done. Series diverges. The terms go to 0, proceed to a new test. Our test here is going to be the integral test. So we're going to let f of x be x e to the negative x. E to the negative x itself is decreasing, so multiplying it by x is going to keep it decreasing, and it's continuous. Continuous, positive, and decreasing. Always check that as well. Again, we don't want the ends to turn up and fake us out. So we can integrate x e to the negative x, but how?
By part.
By parts. We'll take u to be x and dv to be e to the negative x. So that du is dx and v is minus e to the minus x. And so I get the limit as n goes to infinity of uv, so minus x e to the negative x minus the integral of v. V is a negative e to the negative x. I'll make that a plus in front. Du is dx. And I'll worry about the bounds after I complete the antiderivative. But that last integral is going to give me another factor of minus e to the minus x. So I'm going to evaluate the limit as n goes to infinity of minus x e to the minus x minus e to the minus x evaluated from 0 to big N. So to help me evaluate that, I'm going to factor out an e to the negative x. I'll even factor out the minus sign. Excuse me. Is that okay? Did my factoring do okay? And again, to make the limit part easier, let's take that e to the negative x in front and put it on the bottom as e to the positive x. So let me do that here. So I have n plus 1 over e to the n with the minus sign in front. Then I subtract, so the minus sign with the subtraction gives me a plus here. 1 over e to the 0, so that's going to be a 1. Okay, so n is going to infinity. What's happening to n plus 1 divided by e to the n? Goes to 0 really fast because e grows faster than n, right? So this goes to 0, then 0 plus 1 gives me a finite value of the integral. The integral converges. That means the series converges. All right, so I'm going to put 3 of them up here. You're going to tell me converge or diverge and give me a quick reason why. Yes. There's three. Three quickies. Friday afternoon quickie. Math-wise.
No, you don't.
I have no idea what's going through your mind. Who wants the first one? Volunteer yet? Is that volunteer? Is that what I said? I do.
I'm thinking I'm very done, so gotta give it. I'll start at number 3. that way.
Okay, you can have number 3.
By the time we get done.
Is Diverge
Which one?
number 1?
Number 1 does diverge because
It's like goes to 0, or it goes to non-zero.
the limit of that thing goes to what?
Even if it-
E to the 1.
Oh.
That one, if you take the limit, it'll go to e to the 1. That's the definition of e.
Right.
Right? Usually it goes to whatever's up here. But something in front of the case then change it as well. But if you take the limit of this thing, it diverges because the limit as k goes to infinity, 1 plus 1 over k to the k is equal to e, which is not 0. That's our test for divergence. Make sure you're able to show that that goes to e. Remember, that's going to be a logarithmic type manipulation to get the limit. Okay, next one. K to the -3.
goes to 0.
Let's go to 0. So that means I know nothing. But if I write it with positive powers, now I know something. Counter is raised to a fixed power. What's the name of the series? P series, powers bigger than 1, it converges. Okay? That one's 1 in disguise as well. Think of 4 to the 1 minus k as 4 to the 1 times 4 to the minus k. Right, when you multiply like bases, you add exponents. 4 to the minus k means it's in the denominator. Anything? Converge because?
Because if you take the lemon and right there, once you plug in.
Right, limit goes to 0 tells us nothing. Limit goes to 0 tells us nothing. Limit goes to non-zero tells us it diverges. Limit goes to 0 tells us nothing. If the limit does go to 0, we gotta try something else.
Geometric.
This is a geometric series. I got a number and then the power. If you run out the first few terms, the first term is 4 over 4. The second term is 4 over 4 squared. The next term is 4 over 4 cubed, 4 over 4 to the 4th. So you can see that I'm always multiplying by 1/4 to get the next term. So this is a geometric series with r is equal to 1/4. And our conclusion is, since r in absolute value is smaller than 1, the series converges. And since we know what it converges to, let's whip it out. A over 1 minus r. A is the first term. 4 over 4 reduces to 1. So I have 1 over, when I say R was 1/4. So 1 minus 1/4 is 3/4. 1 over 3/4 is 4/3. Okay? So learn these basic ones, learn your basic integrals, because what we're going to do on Monday is a pair of comparison tests. Right? You've always been told if it looks like a duck, if it quacks like a duck, it probably is a duck. If it looks like a convergent geometric series, but is not quite a geometric series, it's going to converge if the geometric series that it looks like does. Or it's going to diverge if the geometric series it looks like diverges. We make comparison tests. So spend some time this weekend, starting now, doing your homework. I put some on web work. I've got some graded homework up here. For those of you that turned in some papers. Are you okay at home? Let me see. I probably didn't give you enough to see everything here. Good. Oh, you can't see that over there? Can you? That's okay? Where did I put the papers? All right, that was 20,000.
Oh, it's not kind of-
Still here. Yes, sir. I can. Let's do it. Let's do it. Sure. We're taking the limit. Start with that marker. K goes to infinity. 1 plus 1 over K. Okay. So as K goes to infinity, this term goes to 0. So this behaves like 1 to the infinity. It's an indeterminate exponential form. So we pretend we know the limit, call it L. And then we take the natural log of both sides. That allows me to pull exponents down to the front of the logarithm. Now as K goes to infinity, this goes to infinity, that goes to 0, so this goes to 1, and the log of 1 is 0. That's another indeterminate form. We fix that by taking the K in front, putting it on the bottom as a 1 over K. Dividing by a fraction is the same as multiplying by the reciprocal and vice versa. But now this has the right form to let me do L'Hopital's rule. Again, this goes to the log of 1, which is 0. 1 over infinity is 0. So it has the right form for L'Hopital's rule, which says take the derivative of the top, oops, divide it by the derivative of the bottom. So the derivative of log of u is 1 over u times u prime. 1 over 1 plus 1 over k. And I'm going to take the derivative of 1 plus 1 over k and get negative 1 over k squared. But when I take the derivative of that one, I get another negative 1 over k squared down here. And they'll cancel. So all I gotta do is take the limit here for what's left. K goes to infinity, 1 over infinity goes to 0. So this behaves like 1. So now I have 1 is equal to the natural log of L. Get rid of the logarithm by exponentiate. Too fast? So I put one of those on your web work as well.
Cool. When did we ever learn that?
Section 4.5 in calculus 1. L'Hopital's rule.
No, not L'Hopital's rule.
So this is in the same chapter, L'Hopital's rule.
We learned about E and L'Hopital's rule.
Uh-huh.
I've listened to this, right?
You still have your calculus book?
Yeah.
Go back and look at that section. I think it's 4.5, maybe 4.6, somewhere in that.
Finally
neighborhood.
get to open up.
4.5. Because they have lots of examples of different indeterminate forms. Other than 0 over 0, infinity over infinity, there are all those other ones where you have to do some other gyrations to get them to where you can do L'Hopital's rule. So you can refresh your memory on those. Uh-huh. I go right too fast for you today, Jeremy.
I'm just incredibly tired and I decided to take it slow and learn instead of rushing.
That's fine. We need to go put anything back up here on that board. Did I erase something you needed?
No, I was just